Hello everybody, let's get started for this week, day 11 of the class. So we are now starting to learn basics of this MIPS assembly programming, and we start with these directives, learnings, and also your different arithmetic and logical operations that you can do with MIPS. I'd say classify that as a data manipulation type operations. And then we'll move forward in next successive two lectures. Two more important thing. One is branching and decision making in the program. Another is the implement the function on top of this MIPS language so that we can reuse some of the part of the code. That's the whole purpose of having function in any programming paradigm, whether you think of the high level or low level, it doesn't matter. Functions concept is very similar. So with that respect, do you guys have any question or anything for me to discuss with? I'm looking at a discussion if there is any new. Seems like there is none. Okay, let me see. Then why don't I just grab my poll and see how did you do anything? Prepare yourself for this class or not. I'm launching this poll for a minute. You can answer anonymously. It's okay. I think this is anonymous is okay here. Let's see. Okay, I think all of you have done with this poll. Let me share the result with you. 40% of the class said you have reviewed the lecture videos and lecture notes for today's topics. Two of you said no, none of them. Please make sure you review before come to class. Otherwise, this discussion may seems very foreign to you. Some of them, 10 of you, half of the class said some of them you have reviewed. Please make sure you to review the full one, like first to last of these topics. Well, the next one, have you noted your queries in corresponding discussion? 55% says you don't have a question, 45% says no, means you may have a question, but you have not put that in your discussion page. So saying that, let me see if we don't really have question. Let me try to give you some hands-on on the addressing modes. That is the very first of this lecture topic, different addressing mode supported by the MIPS processor. And regarding that, let me see. Is there Prabjit Dhillon? Prabjit Singh Dhillon? Maybe, let me see if he's on. No, he's not on. Okay. Okay, how about Ekta Halani?
Hi.
Hello. Hey, Can you tell us what are the different addressing modes that you have learned in this chapter?
So we learned register addressing, base displacement addressing, immediate addressing, PC relative addressing, and pseudo direct addressing.
Okay, do you want to pick up one and just explain what you did you understand by one of the addressing mode at least, if you want to explain?
So in immediate addressing, so in that addressing, it is where the operand is a constant within the instruction.
Okay, okay. So do you know any example of that, or it's fine if you don't know. That's okay.
Um, I don't really know any examples.
Okay, there. Yeah, a couple of them we have did in the class. Like for example, add I. I think I have mentioned it previously, but anyway, probably you haven't noticed that closely. That's okay. So this one, I would say, let's try to see if we can explore and what really it means in terms of when you are using an data manipulation instruction in the MIPS assembly, or like a control instruction like compare and jump, or jump, that kind of instruction. What the addressing modes involved there. Let me share my screen with you. Okay, I'm sharing my whiteboard. All right. Okay. So, as Hector said, like there are a couple of addressing modes involved in our in the MIPS assembly language, and process. It's not assembly language specific. I would say it is more like to do with like how the processor access operands and information per instructions. That's what is under discussion here. So we have like five of the instruction that MIPS processor supports, right? They are like a register mode, and then it's called it's not register, but it's called a base or displacement addressing. I'll just put the name base. And let me put displacement. Why not? Displacement. Okay. Okay, and then we have immediate, and we have pseudo direct, PC relative. Like, let's put the PC relative first. PC relative, and then let's put pseudo direct. So these are the different modes. These are the different addressing modes that this processor supports. And then we need to find out what are the different, these are, let's say, five different instructions that we gave here. So what are those instructions involved? So that's the discussion I'm going to do now. So basically here what is going on is this. Let's first consider this guy. Add $S0, $T1, T2. So this means really it is you read from the value of from the register T1 and T2 add them up and store it into the S0 register. So that means this instruction involved only register accessing. Like it does not access information from anywhere else. It's just purely register bound instruction. So it's basically is going to be a register mode instruction. Let's make a nice table there. Okay, so this is register mode. The next one is add I, $T1, $T3, and 10. So this one is telling that, hey, get the value stored in T3, add them up with 10, and these 10, remember the immediate instruction format. This 10 is embedded as a 16-bit value within the instruction machine code itself. So that is the immediate type access, and then store the addition value into the register. So that's a register type access as well. That means these involve register access and immediate access. With the same notion, the next one, load word, it involves, so I think this is the first, no, not the first time, actually we have encountered load word is syntax in the previous lectures. So it's really telling that access the value stored in S1 means immediately it is a register. It would be a register bound operation, register access. And then add that value with 12. This 12 being again embedded in the machine code of this instruction. So it's the immediate format. So that means immediate addressing is involved. Then you access the memory from that instruction. So let me just put that in words here. So it's really telling me that S0 stored the value into S0, accessing from the memory with a register value S1 plus 12. Okay, so this part really gives me the immediate access mode of this instruction. And these two parts, we're accessing the register, so that become like register mode. And then this part, we're accessing the memory, and we are accessing the memory in a base displacement order. Means there is a base register. We take this a base register and add an offset on top of that to create an address to be accessed from the memory. That's a base displacement mode. So we do that, and this one is done. This one, I think, yeah, these are all the modes that's involved in this instruction. By the way, there are more types of like memory access, like style, apart from the base displacement. For example, there can be instruction which access the memory address directly without further computation, but MIPS does not support it. For other processors like x86 processor, Intel processors, some of these other processor, they may have instruction like that, which involves other style of memory access. MIPS is a processor which only support base displacement style addressing for data access. All right. Questions so far? Before we move on to D and E?
Professor?
Yes.
Yeah. The R open parentheses $S1 close parentheses, that's referring to the value stored in S1, right?
Yes.
Not the address of S1.
Not the address of it. There is nothing
I see.
called address of S1. S1 is a register.
Ah, yeah. Got it.
Okay. Now, the next one, JL my proc, right? JL my proc, if you look at your MIP screen sheet, it basically says, I believe, $RA. So this guy has two parts. One is making the $RA return address. So don't try to understand what this return address means and what is that. Just take it at some value. It stores some value into return address. We'll discuss this part, return address and $R usage in conjunction with the function implementation in the MIPS. Okay, so let's just think that some value is being stored, and then it changes the program counter. Remember, program counter is a special register. Program counter with some with address of this label myproc. Remember, like each label is associated with an address, so it basically change the program counter value, load the address of this myproc label. So here it is involved. See, it is involved actually in register access. It's just writing back into some register. So it involve a register, okay? And this one, if you look at your green sheet page, this address being constructed with respect to the PC, current program counter. So you can say that this is like a, this involves, like this is the PC, my new value of the PC. It involves some part of the, or okay, let me say this way, in a mathematical term. It's a function of the program counter current program counter, okay, and this myproc level, whatever that comes up with that some value. Okay, we'll determine that in today's discussion. We'll see what are these, but it is more like involving the PC itself, the current value of the program counter, and the next value program counter is a function of the current value of the program counter and the myproc. So it is more like a PC relative. And then the last but not the least is B equals $2.3, or maybe it should be S2 S3. Okay, let me just change this thing. This is S2 S3. Okay, so this one is more like if $2 register content of the $2 equals register content of $S3, $S2, $S3, then jump to level L1. Okay, so here you see it's already involves register access. Both S2 and S3 are access, so definitely it involved in register. And then it is again like something like PC next equals, it's a function of PC current. Hey, by the way, the previous one I did put a cross in the wrong position. It's a pseudo direct. Okay. Now it's a PC current. PC current is a function of PC current, and L1, but in this case, we call it a PC relative. I'll explain in a minute with another example why it seems like they are both like a function of PC current and myproc, and here also function of PC current L1. I'll explain what are there are difference in two modes, but just for not for the discussion as of now, let's take this is a relative this PC next is a relative value with respect to this PC current. Okay, this is a relative value. This is relative to PC current with some indices and all this stuff. And this guy is PC relative mode. One point to note here, interesting point. If this example D was given as just a jump myproc, like instead here, if it was given like a J myproc, that instruction does not involve this guy. Okay, it just involves this part. It does not access anything like a array or something. So for that case, it is not of registered type. It is a pure pseudo direct type in that case. Question.
Professor, could you repeat the full form of BQ?
BQ is the branch on equal.
Could you repeat that? Your audio broke out for me.
Sorry, branch on equal.
Branch on equal. All right. Got it. Thank you.
Okay. All right. So far, so good, everybody on the same page on the addressing mode.
I think so. We just have to review it.
Yes, Brian.
I was saying, like, yeah, I think we get it, but have to review it afterwards.
Yes, please do that. So now let's do another example. Let's see how these addressing modes, especially these two, like the PC relative and pseudo direct, how it is involved in determining the machine code, like how the assemblers treat it. Okay. For that, let's pick an example like this. Let's see. Okay. Let me share my screen first. Okay. Now, in this example, okay, let me put some spaces just to make sure. Now here, what we are saying that there are a bunch of instructions there, and it is placed at, let's say these are the corresponding addresses, instruction like text part of the memory. Those instructions are placed, but those are not placed like this literal of add I. They convert it into the machine code and then place the machine code. So you all know, I hope that by this time you guys all know about this conversion into the machine code, like this the first one, right? The add I. These are simple. We can do it. Right? This part. Hopefully, you guys can you know that these are simple. Our consideration is mostly this one and this one. One is a jump, other is a B equal. Some instruction involved that. Now for that, what we need to do, first of all, we need to look at our MIPS green sheet page. So first of all, this is a immediate type. So let's look at this. B equal is an immediate type, and immediate type format is this. We all know, probably know that, or you can actually look at the green sheet page and come up with that. So it is an opcode. So this is the opcode. Then RS, RT, and immediate. So opcode.
Oh, Professor, the PDF is blocking the actually wait, leave.
Okay, sorry for that. Yeah, or you can separately open your this Google whiteboard. You can go there separately and look at that. Okay.
I just realized that and I was starting to do that.
Okay, RT, RS, and immediate. That is, sorry, RS, RT, and immediate. And this is like 6-bit, 5-bit, 5-bit, 16-bit. So for this, we need to fill out these different forms. Now from your table B equal, our code is 4 hex. Okay, 4 hex is, okay, let's say this is 4 hex in 16-bit. Okay, and then we need to see what are the RS and RT. For these, you need to actually consult another page which actually defines the format. So look at this B equal format. The first one is RS and second one is RT. So my RS, so this is my RS and this is my RT here. So the RS and RT. So S1 is my RS and S0 is my RT. And what are those values then? We cannot put literal. So we look at this table in the green sheet and see the S0 to S7 are marked as 16 to 23. Means S0 is 16 and S1 is 17. So RS is S1, which is 17 in decimal, and RT would be 16 in decimal. Now question become, what is this guy? What is the immediate? For this, we need to look up for another definition on this table. It says that, first of all, look at the function. If RS equals RT, content-wise, then PC equals PC plus 4 plus branch address. The functionality, it's telling the functionality as, let's do this way, program counter new equals program counter current plus 4 plus branch address. Let's call it BA, branch address, okay? And let's go into the branch address definition. Here it is, branch address definition. What is BA is 14 immediate 15 followed by immediate bit pattern followed by 2-bit of 0. So what does it mean? Let me first explain. To listen carefully. It says that take the MSB of immediate bit pattern. This is 16-bit bit pattern, 0 to 15-bit index. So take the MSB of the immediate field and replicate for 14 times. So it is kind of a sign extension of the immediate field. But instead of extending 16, extend till 14. Place the immediate bit pattern and then place 2 zeros out of that. Okay. So from here, what we need to do really is to calculate this IMM value and place that bit pattern onto here. So far, so good. Any question? Okay. Now, concentrate on these addresses. Now you need, these addresses are important. So it says that if it is a jump condition, means they become equal, it need to, program counter need to come from here to all the way here, right? So this is my jumping from here to here. Control need to take care of that. So my PC new, okay, this guy is hex 0040 001C. PC current is what? PC current is this guy, right? Which is 0x, which is hex 0040 000C plus 4 plus BA. So from here we can solve this equation, which is pretty easy, which is saying that this is BA equals hex 004001C, not plus, minus hex 0040 000C minus 4. This one is 010 minus 12. 10 hex is 16 in decimal, so it is 12. BA is 12. But our problem is not solved yet. How do we get from BA to my immediate value? We get it by BA divided by 4. Okay, so this is a crucial point to please note when you calculate the BA branch address. Okay, so it's more like you are calculating the offset, and that offset being BA by 4, which is 3. Why so? I'll explain it. Okay, but let's complete our patterns here. Machine code 3. Okay, so we need to place 3 on these, and then we calculate these bit patterns. So your 6-bit hex, 6-bit hex is what? This is 0 0 0 1 0 0. Okay, I think I can make it bigger. And then 17 in a 5-bit, which is like 0 1, no, 3 is 18, 4 is, okay, 1 4 1 2 4 8 16. Okay, so it is more like 1 0 0 0 1, right? 1, yeah, and 16 is 1 0 0 0 0, and 3 in 16-bit 2's complement form is 0 0 0 0 0 0 0 0 0 0 0 0 0 0 1 1. So my hex code would become, let's just divide, group them by 4. 4 1 2 3 4 1 2 3 4 3 4. Okay, so hex code just has become 1 2 3 0 0 0 0 3. Okay, so the machine code for this guy, let's write it down. 1 2 3 0 0 0 0, 3. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. We can cross check it with the same program. We can assemble it, the same program into our MIPS simulator. And you see here is a BQ, S1, S0 exit. And here's the machine code, 123000003. It's exactly matching what we just deduced. Question so far? Okay.
Could you
Then,
explain the the extension that we did? We took the 14, we took 14 times of the 15th.
I'm coming
So,
to that.
no, okay.
I'm coming to that. Now, think like in a processor perspective, processor is getting this machine code, right? And it slice and dice it, different parts, and it gets the individual parts. It sees that, okay, this is a B equals, so I need to access these two register and compare the value. And if that comparison is true, or is that comparison condition it become true, then I need to jump to some address. My PC new would become something. Okay. Now, what is that something? That something is this guy, which is PC current, which is 0040000C plus 4 plus BA. Okay. BA is what? BA, you take the immediate value, which is this part. Okay. And pick up the MSB of that, make replication of that 14 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Why don't I just use a different color there? So it's the extension. So let's use a black. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 12-bit, 13, 14, followed by the immediate pattern, okay, immediate pattern, which is coming from the code 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, followed by 2 zeros. Let's put followed by 2 zeros. Okay, now what is this? This one become like 4, sorry, 0040 000C plus 4 plus, this is what? This is 12, right? So this is 0040000C plus 16, which is in hex is 000400000C plus hex 10, which is 0040 0040001C. And now let's see this one, this address is this address. Is it clear, Rahul?
Yeah, that part is clear. What I'm not, it's not about not understanding, it's more of curiosity. Why was this particular formula chosen, or how did this formula come about that this formula works? Because
That's a
right
very,
now, to me, it's like this is just some abstract formula pulled out of thin air that we know works and we're using it. And that's difficult to remember. So
okay.
if there's a reasoning behind that formula, it'll be easier to remember and understand the topic.
Okay, that's a very good question, Rahul. Okay, first of all, you see, let me explain about this one. Why this is 2-bit 0 extra added there. You look at these addresses, right? They're all divisible by 4. All divisible by 4. And any bit pattern, like if it is divisible by 4, which is means like a value, let's say some arbitrary value x divisible by 4 is basically x left shift by 2-bit. Okay, so that is the first thing. Second thing is that since they are all divisible by 4, to make the range of this jumping from one point to another, we can maximize by maximizing this guy, right? This guy has a specific limitation, what values we can provide there. It is 2 to the power 15 2 to the power 15 minus 1, right? This is the range of this immediate form. That means we can only specify a value, an index value of these, if we just want to go with pure indices. Like pure indices means like this becomes like index, like you just whatever BA you come across 12, let's say you put there. Instead of doing that, since we know these addresses are going to always to be divisible by 4 by construct, by the architecture itself, then we can actually increase the range of this index by dividing it by 2. Because we know for all this bit pattern, by LSB 2 bits is going to be 0, all of them. You change this guy to a binary, you will see the last 2 bit is always 0 for any instruction address. So that redundancy is being just eliminated from this guy and saying that, hey, whatever index value we come up with, we just shed off the last 2 bit and put it under immediate, and that actually made my jumping range more than if we directly use the index itself on the immediate field. Is it okay so far, Rahul?
So far clear. So far this is making sense.
Okay, so this is a trick to increase the range of my jump, how far we can go back and forth. If we would put that index value directly here, it will limit us a little bit less than what we can do by eliminating the last 2 bit, since we know the last 2 bit of this all instruction address going to be all zeros. Last 2 bit is all 0, LSB side. Now the second part, why it is due to the hardware. Okay, we cannot do anything there. It is always like that, and hopefully when you go to CS147, if you at least take class from me, we will design this along with that, like assumption. You will see under the hardware itself, it is fixed value there. PC, next value of PC is always pre-calculated as PC plus 4, because we know if it is a serial running, like without any jumping or anything, next value is going to be 4 more than this current value. So we always pre-calculate that next address. It is coming from the hardware. All right.
So finding in the hardware implementation, finding the PC with the BQ instruction is a 2-step thing. First, you take PC current plus 4, and then you take PC current plus BA.
Yes, PC current
I see.
4 plus BA, like 2 addition.
I see.
Okay. All
And
right.
go ahead.
Yeah.
One more question on the
Yes.
same thing.
Mhm.
How does the I mean, the most significant bit extension, how does that always work out? Why does that extension always work out?
Uh, this is like, remember our discussion with the sign extension of values?
Yeah.
Like, so here, if it is a -3, let's say it was jumping back instead of jumping forward, it was jumping back. So my indices would have a negative from the current PC. Then your 2's complement form always guarantees that previous bits are all one. Like from MSB side, bits are train of ones and then followed by 0, 1 pattern. So that's why, like when you actually extend it to the 32-bit, you want to take the MSB and replicate that. So that's what exactly is happening right here.
Okay, so the extension is only for recording the the
Maintaining the sign because,
maintaining the sign. It's
yeah,
not for like trying to increase the range or
no,
anything like that.
no, it's the maintaining
I
the
see.
sign because PC current is 32-bit, whereas this immediate value is 16-bit. We need to construct a 32-bit out of that. So we need to do an sign extension there.
I see. So effectively for the effectively for the numerically only the 16 bits are used. The
Yeah.
remaining 16 bits are just to preserve the sign action. I was trying to wrap my head around the way to figure out how the remaining 16 bits could be used up for numerical values.
No, you cannot do that. Yeah, yeah. It's so inherently this BEQ, this PC relative addressing is basically limited where you can jump from one point. So it is so long jump are not permitted. Okay, long jump are not permitted, and that's why also in the high level programming, one thumb rule is that you keep your function as small as possible. You do not like make your function like a 1,000-line function. It's sometimes it actually physically can slows down your runtime on that function. So keep it short so that it's always BEQ is always in the range. Otherwise, compiler need to do something special which will slow down your program. So keep your function or code short, basically. Avoid the long jump.
I see.
Okay, all right. Now let's take 5-minute break. Then after that, we'll come back with that J loop, the other instruction, how that pseudo direct works out.
Professor,
Yes.
so I've just got some more questions now thinking on this thing. Can I ask them right now, or should we wait after the break?
Let's take 5-minute break and then you can ask.
Okay.
Okay, let's resume back. Rahul, you have had some question.
Yeah, so mm, uh, all the addresses, I mean, every address in the memory can be stored in a 32-bit word, correct?
Yes.
So is there a branch on equal that does not use the immediate value but instead uses a value stored in a register instead?
No.
That branch on address would be able to jump anywhere it wants to, right? Without the limit of 16 bits.
There is something called jump register, JR, but that is more like an jump directly with respect to a value stored in the register. So it
Okay.
won't be like something like a compare and then jump.
Okay.
And I think what you are saying, maybe you are thinking that, hey, why don't we, as a instruction, like let's say b equal s1, s0, and let's say $array. Why don't we do that kind of thing to jump, long jump in that way, right? MIPS does not directly provide that because it don't need to, and it is sufficient to have this kind of limitation there. It's already quite a big. It is 2 to the power 16 altogether, to and fro. That means you could be able to address from a point up, almost like 2 to the power 10 is 1 kilo, then 32, 64, 64, no, 32K up and 32K instruction down. So 32,000 instruction up and 32,000 instruction down, you can already access through that. So if your program is longer than that, then you have a problem basically.
Okay.
Okay,
I
you
see.
factor your code anyway. So that's the one reason. And how the long jump is treated in that way, basically what compiler does, it actually inserts some intermediate code. It make a short jump, and then it uses that JR, jump register instruction, to go to that further point, which actually can hold all 32-bit of address, all of them.
And is this done by the assembler, like a pseudo instruction, or
No,
did you say
that's done by,
compiler does it? Could you repeat that?
that's done by the compiler.
I see. So that's done in the compiler for high-level languages.
Right, right.
I see. Thank you.
Okay, then let's move on to our next one, is that J loop. How do we do that? Let me share my screen again. Just one. Okay, and here we are again need to consult our green sheet page, right? Jump has a code of 2 hex. It's a J type, and function is simply PC equal to jump address. So, and all we know is here, we know that jump address is 6-bit of opcode and 26-bit of the address, what they call. Now, how it plays out in determining your machine code for that one. I'll come back to that green sheet page one more time to tell you what is that, how the address is construct, where it can be done. But right now we want to do this. Hey. Okay. So we are now looking for this guy, which essentially send control from this to this guy, right? Okay. This one, from this to this. Okay. And we know the format is opcode with some 26-bit of address. ADDR, opcode, 6-bit, 26-bit. An opcode we know for the jump it's hex 2. Question is, what is this address become, right? That is our question. And we know my PC, which is supposed to be PC next, let's mark it like that, is my jump address. Let's call it JA, jump address. Now let's go back to our green sheet page again. It says the jump address is PC plus 4. This is PC current plus 4. And you take the 4 MSB followed by the address bit pattern followed by 20. Again, this 20 is to maximize where we can jump because all our instruction addresses all our instruction addresses have 2 zeros at the LSB side always. No matter what the instruction is, it is a common observation. So we skip those 2 zeros and hardware assumes and add those 2 zeros on a runtime. So this jump address is equal PC, I would say current plus 4. Now out of that we pick up 4 MSB followed by the bit pattern of address followed by 2-bit 0. So this is my next address. So out of these, that means we need to figure out what this bit pattern would be to place while assembler is determining the machine code for that instruction. So now we know in this example, your PC current plus 4. So your PC current is this, plus 4 would be this one, right? So it is 0 cross 0040 001C. And PC next is going to be this address, right? So which is 0 cross 0040 000C. Now let's expand those into 32-bit pattern. Okay, so your PC current is PC current plus 4. It is 0000 0000 0000 0100 0001 and C is 1100. Okay, and your PC next has to be 0000 0000 0100 0000 0000 C. C is what? C is 1100. Okay. Now, according to this formula, what we need to do is shade off these 2 bit, okay, and pick up rest of the 26-bit. And put it under address. So your address is going to be 0000 0100 0000 0000 0000 sorry 1100. Okay, 1 2 3 4 5 6. Oh, my bad. And to shade off these two. So that gives me 26 bit. 1 2 3 4 5 6. 24 bit plus 2, 26 bit. All right, now we are in business. And this 6 bit is 000010. Now we make, so this become your machine code. This become your machine code. And what's in the hex? That would be like these 2 zeros, 2 zeros. Okay, your hex is going to be 0 cross 0 8. So this is 0, this is 8, 1 0 0 0 0 3. 1 1 2 3 4 3. Okay, let's check if it matches. Yep. Look at this. J loop 0 8. Hey, 1. Why did I miss it? Oh, I missed it. Yep. 8 1. Next one is 1. 1. Okay. 081 0 0 0 0 3 0 0. I missed 1 0 there. That's what happened. Let's check 1 2 3 4 5 6 7 8. 32 bits. So that's become your machine code. Now, when processor gets this machine code, then what it does is basically dice it with this format. Okay, 6 bit for opcode, it knows is a jump. Then 26 bit it picks up, and that 26 bit would give me this this guy, right? And then, so let's write it down. So that 26 bit coming from the address is 0 0 0 0 0 1 0 0 0 0 0 0 0 0 0 0 0 0 0 1 1. Then according to the format, it will add 2 zeros at the end, and it will pick up 4 MSB from the PC current plus 4. So that will be added into my target address. So this is my PC next is constructed, and this is equals 0 0 4 0 0 0 4 0, then 0 0 0 C, which is this guy. We just jump as a next instruction. Question? So this concept.
Professor,
Yes, Rahul.
could you explain that open square bracket 31:28 close square bracket?
This one
Is that the extension? Because over here the extension is not a negative extension, right?
no. This
Even
is
though
your,
we're going back.
no. You are picking up this whole thing PC current plus 4, this is 32 bit. And out of this 32 bit, you are picking up bit 31 to 28. So this 4 bit.
I see. And adding that to the address thing. Okay.
Yeah, appending that to the determining the next address. Okay, so that's why.
Could you repeat that just one more time?
Yeah, so basically so your PC current plus 4, that's a 32-bit value.
Yes, yes.
This 31 to 28 means you pick up bit from 28 to 31 of this 32-bit pattern. So this is your 0th bit, this is your 31st bit. So you pick up bit 28, 29, 30, 31.
Right, that explains a lot. Thanks.
Okay.
Professor?
Yes.
So just a question regarding the implementation. Right? Suppose the current suppose the J instruction is present at the current address, which is 0001, and then all remaining zeros. So we're starting out with that. Okay, and you're trying to jump one instruction back. So that would be 000 and then FFFFF. So if we're following that way, we take the first 4 and add it onto and we take the first 4 bits and then we have the address bit. So the first 4 bits will be 0001 and then something, whatever the address is going to be. And the address, is the address always going to be positive, or can the address be negative here?
No, the addresses are all positive unsigned, but I think what you are trying to say is if there was a 1 here, right, and I want to go to the next one, how this scheme or how this strategy works.
Yes.
Okay, that's a very good question.
When something in the first 4 digits are changing, because that just looks to be a complete copy paste over there. It's not accounting for the change over there.
Yeah, now we look at the usage.
Oh, I think I just realized. No, nothing. Please continue.
So your hex is basically, it is starting from 100 address, like something like 1 here means 100 something, which is a part by convention, which is a part of the static data. Your text program cannot go beyond that. So it is guaranteed that these 4 bits will always 0 by that convention.
I see.
Okay, so your thought process is correct, right? What if that is there? But this is constrained by your usage model. So you really cannot place any data. Operating system should not go and place a text code inside the static data region. And that will break up this part assumption, and that will cause a problem as you described.
Wait, so even the program, even the MIPS, even the assembly language is dependent on convention?
Yes.
I thought okay.
That's why you cannot just like take one assembly program, assemble it, machine code, and just run it onto another processor. It is basically tied to a processor convention.
It's tied to both the processor's hardware and the conventions people use on that hardware.
Yes, and that's why this convention is part of the instruction set architecture. Whenever we talk about instruction set architecture, it is just not the list of this instruction. It's also the memory usage, assumption, the registers, and all this stuff have become part of that definition. And your assembly program must follow it. And thus the compiler, thus the operating system. And all the upward stack in the whole computing system should follow that convention.
I see. I was under the assumption that we can write our own programs ignoring the assumptions and ignoring the convention, and we'd be fine as long as our program works in isolation.
Well, if you don't involve the jump, for example, in your program code in the static data region, you should be fine.
I see. But there are instructions that are dependent on conventions, not just collaborative projects that depend on convention.
Yeah, exactly.
Okay. Neat.
So now, hopefully, you now find out as we started our discussion with this one, why PC relative and pseudo direct, they are different, but they are all function of PC current and somewhat this level address because of they compute differently. Your jump, that PC relative addressing, basically involves the value of that program counter, and as it adds, do mathematical operation on top of that as if it is indexing with respect to that program counter value, whereas pseudo direct is not involved any kind of indexing or that per se, just picking up a part of the current program counter and just patching it up on top of the 26 bit. So that's the difference between the pseudo direct addressing mode and the PC relative addressing mode, where PC value is really important. Here it is not so much important. It is 0, 0, and it's all by convention. It is 0, 0 anyway. So instead of taking up from the program counter that higher part, it could have just blindly put zeros here. That would be also okay. But somewhat like the hardware designer wanted to keep it flexible in case thought process like Rahul come up, and then they can switch around the situation like this. So, but the fundamental is that the address determination is different, even though PC program counter is involved in both the pseudo direct mode and the PC relative mode. Okay, I think we are over board 2 minutes. Next day, we'll talk about this branching instruction. Please make sure you review your lecture notes there and review the videos. Very important. All right, see you on next Thursday. One important thing, quiz is coming up. Quiz 3 due this Saturday, will open up on Friday morning. So make sure you all submit it in time. All right, good
For
night.
the lecture, Professor.
Thank you.
Hi.
Thank you, bye.
Can I talk to you?
Professor, the
Oh,
quizzes
yeah,
are
yeah,
open book,
sure.
right?
Oh, let me ask this question first.
Professor,
Yes.
the quizzes are open book, right?
Yeah. It is the same
Yes.
like the previous quiz.
Same like the previous quiz. All right. Thank you.
Okay,
Yes. Yeah.
Oh, yeah, sorry.
Tell me.
Oh, okay. So I need to talk to you about one of my homework assignments.
Uh-huh.
So I'm pretty sure it was assignment number 3. When I did it myself, I double checked to make sure that like the output was perfect. And then when after submitting, I knew that I submitted the right file, but I seem to have received a 0 on the gradebook, and I'm not sure why. Can you go over that with me?
Send me email. Did you send me email?
No, not yet, because I thought I would just talk to you.
No, yeah. All these disputing case, please send me email.
Okay,
So
sure.
I can follow through, okay?
What do you want me to tell you in it though?
Just subject line, add your class code, like follow the protocols there.
Yeah,
and
yeah.
What's your complaint about? Then I'll go and check.
Okay, sure. Thank you.